When examining engine parts, we should first look at the engine block, as it serves as the main frame of the engine. All moving parts are either contained in or attached to it. It contains the cylinders where diesel power is produced and where the reciprocating motion of the pistons is changed to rotary motion. There are 4 design requirements for a Caterpillar block. 1. It must maintain internal alignment under all operating conditions. 2. It must be strong yet compact. Engines designed for applications where size is important generally have a V configuration, as with the 3208. 3. For fuel economy, it must be lightweight. Users consider the weight to horsepower ratio when purchasing an engine. CAT engines generally have slightly higher ratios than the corresponding competitive engine, but are considered a heavier-duty engine with greater potential for rebuildability. And 4, it must be rebuildable. This is the case with the 3208, which can be rebored or sleeved back to standard cylinder bore dimensions. Let's look at how Caterpillar meets these requirements, first in the design and then in the manufacture of engine blocks. Before Caterpillar arrives at the finished product, engineering spends months and sometimes years researching the design which will offer both performance and serviceability. Serviceability is important in matching a specific engine configuration to a particular application. Caterpillar uses an analysis approach to design. Before a design prototype is produced, engineering runs a computer simulation to determine weaknesses on a proposed design. The computer simulates working conditions and isolates stress points. Through this type of analysis, they can design a block which best serves a particular application. After the analysis is complete and an acceptable design is decided on, it must meet both fatigue and thermal test requirements. The fatigue test simulates actual working loads and beyond. Internal pressure is increased to the point where the structure cracks. After the completion of testing, the prototype engine is completely torn down and thoroughly inspected with emphasis on specific structural areas such as the lower case structure and bore areas. If the design meets the test requirements, then it is ready for manufacturing. The key is that Caterpillar spends a lot of money testing and researching the best design which incorporates the most horsepower in a lightweight, strong, efficient engine. From the engineering drawing, a 3-dimensional pattern is produced from wood, metal, or plastic. From these patterns, molds and cores are produced. They are composed of a highly controlled sand and resin mixture. This ensures that interior cavities of the casting are smooth and free from metal and/or core sand debris. This could restrict coolant or oil flow and cause oil and water pump failures. After the mold is fabricated, the next step is pouring. A nickel-chrome-copper-iron alloy is used in making engine blocks, which provides for maximum strength. The heating and consistency of the metal is computer-controlled, and samples are taken to assure proper iron makeup and ultimately a quality casting. The Caterpillar manufacturing process ensures uniform hardness of all blocks and heads. This is important so Caterpillar blocks and heads can withstand without failure the high temperatures and stresses found in a diesel engine. Cummins tests their blocks for hardness, while softer blocks are assigned lower horsepower ratings. Following the casting process, residual stresses are relieved through controlled heat treatment. Without this, cracking will result. Then each block receives a rigid final inspection for cracks and correctness of foundry locators. Here we see the rough casting as received from Mapleton. Caterpillar uses transfer-type tooling to handle the machining of engine blocks. Transfer tooling refers to the automatic movement of the casting through a series of machining operations. The computer-controlled conveying system automatically stops the blocks at the various stations. Critical operations have self-adjusting tooling. In other words, wear on the tools is taken into account and compensated for. Details such as self-adjusting tooling are critical to ultimate engine performance. All machining operations are important, but some are more critical than others. For example, the clearance between the cylinder wall and piston is critical. Too little clearance causes increased friction on piston rings or piston seizing. Too much leads to increased pressure on the rings, blow-by, and loss of engine efficiency. The finish and squareness of the head face is critical. If they are not kept within tolerances, oil or coolant leakage may occur. Additionally, a compression leak can occur which will result in loss of engine power and possible block erosion. We maintain exact print tolerances aiming for exact print specifications. For all block machining operations, exact dimensions are held and monitored for exactness by electronic gauges. Caterpillar uses the most sophisticated equipment available. The DEA electronic testing equipment judges two-dimensional relationships between different areas of the block and provides a 100% inspection of all machined surfaces. Here we see the engineering tolerances demanded and a comparison of these to the actual dimensions achieved. You can see there is a minute difference between the two. This exactness in machining allows for greater dependability, increased reusability, and longer life. These in turn provide users with lower owning and operating costs. Before discussing cylinder heads, let's briefly discuss the spacer plate that's mounted between the block and head on the 3300, 3400, 3500, and 3600 series engines. Placing this steel deck plate between the head and block remedies the need for counterbores in the block, a frequent area of cracking in some competitive engines. Since counterboring removes a portion of the block, it actually removes a portion of the block's strength as well. This weakens the top end of the engine, an area where Caterpillar believes structural strength and rigidity is important. Let's now turn our attention to cylinder heads and talk about the function and design requirements. A cylinder head has three primary functions. 1. It contains the intake and exhaust ports that lead to and from the intake and exhaust valves. 2. It holds the valves and direct injection adapters. 3. It has internal water passages that circulate engine coolant around critical areas such as the cylinder walls and exhaust valve ports. As with blocks, considerable time is spent on head design. A design must be capable of withstanding high cylinder pressure and must have high tensile strength to resist material fatigue and cracking. Each new design must pass the thermal shock cycle testing we discussed earlier. Cylinder heads are cast at Mapleton and are heat treated to relieve stress. Then they are moved to Mossville for machining. As with blocks, the head is handled by transfer-type tooling and automatically moved through several machining operations. Some of the operations are very critical. These include the finish of the head face. If this is not correct, then the head gasket may leak, causing loss of engine power and possible block erosion. Valve guide bores. If these are not kept in tolerance, abnormal wear and breakage may result. Valve seats. If these are not within tolerance, then the result could be valve leakage, loss of power, or burned valves. Here we see the valve inserts installed. The inserts are kept in a freezer registering 180 degrees Fahrenheit below zero because freezing shrinks metal. The tolerances are so precise here that only by contracting the inserts via freezing can they be pressed into the head. Experience shows that this is the best technique for assuring that inserts will not work loose in service and result in serious engine failure due to mislocation or improper seating of valves. As part of the final inspection, all heads are pressure checked for leaks and porosity to assure they will handle the high pressure they are subject to during operation. After final inspection, heads are assembled with mating parts if required for production. Heads produced for parts service are serviced on the assembly level and contain only dowels, inserts, plugs, and guides. All Cat engines except 6.25-inch bore and 3500 and 3600 series have a one-piece head to ensure structural strength and rigidity on the top end of the engine. A one-piece head also allows for a more compact design, so we can put the maximum-sized engine in the smallest area. So a one-piece head is stronger. A good analogy would be to cut the lid of a shoebox into 3 equal pieces. Put the 3 lid pieces on the shoebox and try to twist it. The box twists quite easily. But if that same box had a one-piece lid, it would take a definite increase in effort to twist the box. The solid one-piece lid adds more structural strength to the box. Multi-piece heads are used on large bore engines because of weight and size restrictions. A multi-piece requires greater spacing between cylinders and a stiffer, heavier design. It also has a cost advantage when replacement is necessary. Unlike blocks, there are competitive direct replacement manufacturers and distributors for Caterpillar cylinder heads. IPD, Industrial Parts Depot, offers new and rebuilt heads. Ganassi is an Italian manufacturer of heads and final drive components founded in 1927. They offer heads for several of our engine models. Of course, the major new competitors are those that weld heads. At Caterpillar, we build engines from the ground up. This includes the highest quality blocks and heads in the industry. We believe that details do make the difference.